Today I will be talking about a new window into the universe, observing gravitational waves from astrophysical sources. But before I go into this specific topic, I would like to first spend some time just trying to give an overview of a range of different things I work on, so that maybe some of you will find interest. So basically, I'm a theoretical cosmologist who works at the intersection of cosmology, astrophysics, and also some little bit particle physics. I think I'm mainly interested in trying to study different various kinds of astrophysical phenomenon in order to address some of the really fundamental questions about our universe. So for example, I worked on cosmology, trying to understand what happened in the early universe. So I worked on primordial gravitational waves predicted by currently our best theory about how everything began, inflation. In particular, I worked out how inflationary gravitational wave background can leave some imprint in a large-scale structure, and if it is confirmed with other probes, then this will give perhaps the strongest piece of evidence supporting the theory of inflation and put very stringent constraint on other theoretical possibilities. I also work on relativistic theories of large-scale structure clustering. So basically, if you want to interpret data on very large scales, then you cannot really use the usual Newtonian intuition. So with some collaborators, I clarified what types of non-Gaussianity signatures in galaxy clustering can really be interpreted as some smoking gun for new physics during the inflationary phase. And in addition, I also work on a number of phenomenologies regarding the cosmic microwave background. For example, some accurate calculation of the aberration effect due to the motion of the observer. I worked out that the CMB photons might change its polarization states when propagating all the way to us due to perturbations in space-time. I also work on other things such as the Sunyaev-Sadovich effect. But more recently, I mainly focused on gravitational lensing and gravitational waves and trying to figure out what we can learn about what kind of fundamental questions we can address using these phenomenon. I think tomorrow I will be talking at NYU Physics. I will be giving another seminar talking a lot about highly magnified sources recently discovered in strong lensing clusters. So by studying this new class of lensing phenomenon, we are mainly interested to constrain the small-scale structure of the dark matter, basically on scales much smaller than the scale of galaxy formation. And basically, we find that there are a number of very interesting applications. One is that you can really constrain the any fraction of compact objects that dark matter may be made of. You can constrain the abundance of dark matter halos that are smaller than those hosting dwarf galaxies. And I think this might offer one of the best opportunities to constrain those structures. And you can even constrain in a collective way so-called mini halos, like planetary or subplanetary mass objects that are predicted in some of the very promising theoretical models of dark matter. So if you're interested in this topic, I think I will explain more tomorrow. But then I also worked on alternative sources, cosmological sources, for example, faster radio bursts as lensed sources, and gravitational waves as lensed sources. So today I will explain what we found, what kind of things we can learn from this phenomenon. And in addition, at IES, I'm working with a group of people trying to independently analyze public gravitational wave data. So we have developed some useful data analysis methodologies. So in case people here are interested in data analysis methods, I will highlight those. So I think today for gravitational waves, I will start with a little bit motivation and background knowledge. So according to general relativity, any mass will curve the space-time around it. So now if we imagine that this mass is moving, not stationary, then the surrounding space-time has to dynamically adjust to that. So this causes propagating modes that propagate the variation in space-time metric to large distances. So these are called basically gravitational waves. And now typically we observe these waves from far away. And currently the best way to measure this gravitational wave distortion is using a laser interferometry technique. You basically measure the change of proper length along two perpendicular directions, perpendicular to the direction of wave propagation. So now typically the best sources our universe has are a pair of extremely compact masses, black holes, neutron stars, or white dwarfs. And if the sources are moving with non-relativistic speed, then from far away, the so-called gravitational wave strain is proportional to the quadrupole moment. So if the quadrupole moment is time dependent, then we can measure gravitational radiation. It's useful to understand for this common class of sources what is the qualitative properties of gravitational wave radiation. This is some typical strain signal we will measure in detectors as a function of time. So roughly speaking, this is some chirping signal. The strain is oscillating as a function of time, but then the frequency is evolving. So the signal can be divided into several stages. At the beginning, you just have a pair of masses orbiting each other, and the orbit is shrinking because you're losing energy and angular momentum through gravitational radiation. So then the wave frequency will be twice the orbital frequency, but it is slowly increasing. But then toward the end, the increase of wave frequency accelerates. Eventually, very quickly, the two masses fall toward each other. Now, if you form some remnant, such as a black hole, then this black hole, it takes some time for it to settle down to stationary configuration, so you have additional radiation called ring-down radiation. So now the whole process can be modeled very precisely by combining analytic calculation and numerical relativity simulations. So currently, by measuring what we actually detect in the data and compared to these theoretically calculated waveform, we can extract information about the source. So first of all, the most important thing is how the frequency evolves with time. So if we define some waveform h as a function of time, then we can define the wave frequency by tracking the phase of the wave and see how fast it evolves with time. The foremost parameter we can measure is the so-called chirp mass. It's a particular combination of the two individual masses. And this tells us roughly how the frequency evolves with time. So this parameter currently can be measured quite precisely. Then we can measure a couple of more parameters. For example, the mass ratio between the two black holes. Although this parameter, the error bar, is typically quite large, we can only tell the difference between comparable masses and very different masses. And then there's another parameter we can infer about the spins. So if you have two black holes, then in principle you have two vectors which can point in arbitrary directions. So far, with a typical event, we can measure the mass-weighted average of the spin components perpendicular to the angular momentum. So this is called the effective spin parameter. Now, this is the current observational status of detecting these sources. The LIGO-Virgo collaboration have carried out two observing runs called O1 and O2. So during these two runs, most of the time we only had the two LIGO detectors at Hanford, and at Livingston operating. Now, during the second observing run, only toward the very end, we have the Virgo detector joining. So during the first two observing runs, a couple of black hole merger events and one binary neutron star merger event were detected. So now, currently, the third observing run is ongoing. With most of the time, we have the two LIGO detectors and plus the Virgo detector. So we are, I think, although the final results have not been released, we are expecting many more detections of binary black holes and also several binary neutron star and neutron star black hole merger events. So in the future, we are expecting, in addition to these detectors, two other detectors, one in Japan and one in India, may be joining. So currently, the most abundant sources that we can detect appear to be binary black hole mergers. This is a little bit surprising because we don't really have other evidence that such binary black holes exist in large abundance. And currently, how they form is a mystery. So the fundamental question one needs to address is how we can bring together two black holes to sufficiently tight orbit so that they can merge within the age of the universe. So here, let me summarize that currently we have a number of several class of ideas. So one is that you need to, you form two massive stars. They orbit each other, and then after they become black holes, they tightly, these two black holes tightly orbit each other. So there are a number of ways to get these two black holes very close to each other. One is that you can go through the so-called common envelope phase. So one star goes into the envelope of the other star and spiral in through dynamic friction, but then eject the envelope. The other way is, maybe these two stars, they're tightly interacting with each other, but then they are compact enough that they will not merge before both of them form black holes. But then apart from this isolated evolution scenario, there are also scenarios that form these systems dynamically. So typically you require very dense environment, such as globular clusters or maybe nuclear star clusters. You can dynamically form these binaries through, for example, gravitational radiation capture, or maybe exchange interactions between a binary and a single. But then apart from that, there may be other very special environment we can make these black hole binaries. For example, surrounding supermassive black holes, there might be very thick disks of gas, and these which can efficiently capture black holes and make them find each other to form pairs and merge. So I think currently we don't really have a very clear idea which of these scenarios actually work, or maybe a number of them work. So that is the task of empirically observing these events and trying to match with theoretical predictions. To basically help solve this problem, a number of talented colleagues at IES decided to independently analyze the publicly released O1 and O2 data. So these two science runs. I think the major motivation behind our work is, first of all, we really want to explore if you are a person outside experimental collaboration, but just some ordinary astrophysicist, how accessible the data really is. Like, can you help your research by actually directly applying your theoretical model to data? And then we also want to independently verify what the LIGO-Virgo collaboration have reported. I think this is also kind of important. And finally, we really hope that maybe we will find some sources that show properties very different from what we have already seen. So in this way, we can make best use of the data. So the way to detect the gravitational waves is usually through the technique of match filter. So the idea is that you have very precise theoretical prediction of the waveform, and then you try to find it in a long sequence of noisy data. So because typically the signal is very weak, but then we have quite perfect knowledge of what it looks like. So we basically do match filtering. This is loosely speaking a overlap between the template and the data, but then cleverly weighted by the inverse of the detector noise level, called the power spectrum density. So this is a function of the frequency, reflecting at each frequency how noisy the detector is. The first step in this process is that we need to have a list of all possible theoretical waveforms that we think is relevant. So this is the task of building some template bank so that we can search one by one in this bank. So now we want to come up with some efficient way to construct such a bank, and it's better that this method is very flexible. So there has been a lot of methods people explore, but then I think generally people want to construct some linear space that all possible theoretical waveforms, h of f, in frequency domain live in. But then we think that maybe the best way to efficiently find this linear space is not to consider the waveform h of f itself, because h of f is fast oscillating. But instead, let's write it in terms of some amplitude and some phase. And let's unwrap this phase so that it is a smooth function of frequency. Then the intuition is that as far as match filtering is concerned, this phase is really the important one. You want to be able to measure the difference between two very close phase functions. And maybe the best way, therefore, is to construct a linear space of this phase function rather than the waveform itself. So in general, we can write this phase function as a linear combination of different bases. There will be two trivial bases, corresponds to just some constant phase shift and some time delay. But then there will be some non-trivial base functions that captures what physical signals look like. So we can define some orthonormal problem which depends on the actual noise level as a function of frequency in the detector. And then we can numerically find these basis functions by narrowing down to basically the region where physical waveform live. And then what we find is that the number of non-trivial bases is typically very few, like just maybe 2 basis functions, 3 basis, but no more than 4. And this is kind of intuitive because in any case we were not able to measure many independent parameters from the waveform. So once these special dimensions are found, we just make a regular grid in this multi-dimensional space, and that forms our template bank. So this is an illustration of how we construct a template in the parameter space of masses. So we have, here binary neutron stars, here binary black holes and neutron star black holes. We make several banks because we're using the property that each bank, the number of template is not excessively. We are not like excessively including too many templates so that we pay a lot of price in look elsewhere effect. And the second is empirically we find detector noise transients, they are distributed very non-uniformly. So some of the banks are heavily contaminated while others are very clean. So after that, we can verify that each of the template bank, the template is really accurate and effectual. So now the task is to match the template, match each of the template through the data and register significant triggers in terms of the match filtering score. So if we are able to normalize each template, then we can define this complex number Z, which is the inner product between template and data. So if the data is the noise is perfectly described by Gaussian random noise, then the Z variable obeys some chi-square distribution with a predicted tail. And whatever triggers that stands out of the tail will be interesting triggers. So this is the rule of the game. But then in reality, one has to do a lot of detailed work to get this distribution close to Gaussian as much as possible. One is that the detector sometimes do not really behave in a Gaussian way. There are like noise transients happening. Whenever this happens, we use some technique to detect that certain seconds are corrupted and therefore should be thrown away. So how do we do that? Naively, you would just say, let's just zero these bad seconds. But then that introduced, because the match filtering kernel is non-local in time, so that by doing this naive thing will introduce oscillating artifacts and corrupt nearby data. So the way we do it, so some typical way to do it is use a smooth window function. It usually works very well, but sometimes it doesn't because the noise has very coherent, loud, narrow lines. So these lines are the coherence time is so long that even these smooth windows cannot guarantee that there's no contamination elsewhere. So what we do is we solve some linear algebra problem to find some ideal filter that we can apply to the data, such that after we apply it, the information coming within this bad second doesn't matter at all. So the easiest way to understand this method is just to try to imagine that your noise model is the usual Gaussian noise everywhere, but then within this hole, you have some artificially introduced noise that is infinitely loud. Then you ask question, what will the maximum likelihood of data that is consistent with this noise model? And that is allows you to find this filter F. So another way is to make analogy with CMB. We know that along the galactic plane, the CMB, the primordial signal, cannot be seen because it's heavily obscured by foreground. But then whenever we see some beautiful full sky CMB map, we know that the data coming from the galactic plane cannot be what we actually measure. So it's actually just some reasonable extrapolation from the noise realizations elsewhere. So this is some similar technique. Another problem that we empirically find, is that the assumption of a stationary Gaussian noise is actually not good enough. So the detector level, the noise level, is actually drifting with time. So the evidence is that if we measure the variance of this quantity z as a function of one data chunk after the next, and then we can compute what is the power spectrum of this variance in time. And we find that apart from the expected Zampo noise, just some white noise power spectrum, we also have red noise power spectrum. So this is suggesting that the noise level is fluctuating on some seconds time scale. And this has bad consequences, because whenever the noise is fluctuating more than you expect, you underestimate you overestimate the significance of your triggers, and therefore the tail of this Gaussian distribution is heavily polluted. So actually we propose a very simple method to solve this problem, which is just you empirically measure the variance of this z as a function of time on seconds time scale, and you manually correct for that. So this proves to be very useful and really improve the sensitivity of our search pipeline. So now that we find significant triggers, once we can declare a signal, the next important task is to extract useful physical information by measuring source parameters from the signal. So there's a computational problem involved here, which is you need to compute the likelihood repeatedly, again and again, and each likelihood is like some inner product in frequency space. You have to sum over many independent frequencies. So the major, usually the major problem is that if you do brutal force summation, because the waveform oscillates really fast. So here I show an example of a binary neutron star waveform within some narrow frequency range. Because it's oscillating very fast, so you really have to have very fine frequency sampling, and that is a lot of summation. But then we realized that when you explore solutions near the best fit, all of those solutions actually look very similar to each other. So for example, here, if we compare solutions that differ by some small amount in the parameters, already the oscillation behavior differs substantially. But then if you take the ratio of the two waveforms in Fourier domain, the ratio is a very smooth function. So then that doesn't require excessively fine frequency sampling. So this gives us a way to compute likelihood efficiently. The procedure goes as we first define some fiducial waveform, and then for that waveform we compute some moments in bins of frequencies. And these moments just need to be computed once and for all. And then whenever we explore parameters, we just compute what will be the ratio between the new waveform to the fiducial one. And then that allows us to express the likelihood as a summation of bins instead of many individual frequencies. So here I just give some example. For binary neutron star mergers, instead of summing over millions of frequencies, we have order 100 bins, frequency bins, chosen in some smart way, non-uniform way. And then the outcome is that our approximate way of computing the likelihood, it will make some error, but then we check that the absolute error in the log likelihood is under control. So it is less than, let's say, 10% or 5%. And then we can make sure that this essentially has no practical effect on the posterior distribution of the parameter estimation results. So all of these techniques are now being regularly used in our analysis, and I guess it is interesting to show what we actually found. So we analyzed O1 and O2 public data, and in particular, we searched carefully possible binary black hole signals, the heavy mass mergers, and we were able to reproduce the results reported by the LIGO-Virgo collaboration in O1 and O2, which are indicated as the blue posterior blobs on this plot. This plot is the total mass in the source frame versus the effective spin parameter. But then in addition, we find a number of new events. Some of them, there are 3 of them that are indicated as green here. They are considered very significant. And indeed, another independent group led by Nitz et al. They carry out independent analysis, searching for black hole merger signals, and then they reported a number of significant new events, and we found that the 3 most significant events we are finding agreement with them. Okay, so in addition to that, we also have less significant events with lower astrophysical probability, which are indicated as these yellow and red contours. Some of these events show high effective spin that we don't really observe with LIGO-Virgo events. I think the main picture is that if we only consider the most significant new events, then they really fit into what LIGO and Virgo have seen so far. So basically, most of these events are very heavy. They have masses around 20 to 40 solar masses in the source frame, and not really previously seen in X-ray binaries. And these systems have comparable component masses, although the constraint is so far not very strong. But then they seem to show that they are not spinning very fast. So all of the events, you can see that their high effective parameters are either consistent with 0 or they take low values rather than high values. And I think another very interesting phenomenon is that although we are seeing really heavy events, but so far all the sources are consistent with a upper black hole mass cutoff at around 40 to 50 solar masses. And this cutoff may tell us a lot about stellar evolution, in particular this effect called pulsational instability. Pair instability supernova and pulsational pair instability supernova. So in addition to these 7 events I showed, we also come up with some new data analysis methods to declare additional events. So most of the time, a physical event will have significant signals in both detectors. But sometimes you just get unlucky that in one detector the signal is really marginal. And when it's really marginal, for practical reasons, one cannot really collect all triggers at similar levels. So then this kind of event can escape the search pipeline. So for coincident events, one can empirically estimate the background in a simple way. You just take the data in 2 detectors, you shift one detector relative to the other by an amount that is more than the light travel time. In this way, you just empirically measure the noise background, because any coincidence you find this way cannot be physical. But in the case of so-called single detector triggers, one detector doesn't have a very loud signal, then we cannot do this in practice. So then what we do is we identify these single detector triggers, and then we look back into the other detector to see if there's any interesting counterpart signal. But then in this case, because the counterpart signal typically will be no more than 3 sigma, so we really need to do a proper Bayesian analysis rather than just maximize the likelihood. It makes a big difference. So what we do is we define this score, which is basically fix the intrinsic parameters, the masses and the spins, to be what this other detector suggests, but then try to marginalize over all possible extrinsic parameters consistent with data. And this can be efficiently computed. Once we compute this score for the actual trigger, we also try to derive empirically under two hypotheses. One is that the counter signal is just some random noise. And in this case, we can just slide the other detector and perform the same procedure again. And then in this way, we can derive a distribution. The other hypothesis is that the signal is genuine. So in this case, we again slide the other detector, inject some expected counterpart signal, and then we derive a distribution for these intrinsic parameters. So eventually, we just need to test if the actual measured score is consistent with which distribution. So in this case, we tested this method with one LIGO Virgo reported event and showed that this really works. And then we find an interesting event in which the Livingston signal really stands high above the background distribution, but then there's no loud Hanford signal. So then we perform this procedure and find that actually this event has a false alarm rate empirically measured to be something like a few % chance. And interestingly, the parameters inferred for this event seem to fit with the population of the most massive and the most distant binary black hole mergers. So I think looking to the future, currently O3 is the third observing run is detecting a lot of binary black hole mergers together with mergers involving neutron stars. So definitely when the public data is released, we should be able to apply our technique onto the new data and try to see if we can actually go a little bit deeper into the noise. And also we noticed that many O3 triggers, they fall into this single detector regime, so that we should be able to test how useful this Bayesian framework is in terms of estimating the significance. And then we hope that we can extend the search parameter space. For example, what about neutron star black hole mergers? What about very heavy binary black hole systems? What about systems with very large mass ratios? There may be other types of gravitational wave signals, some of them unexpected, hiding in the data. For example, if you have a jet and within a short period of time accelerating a huge amount of mass, you might generate a pulse-like gravitational wave signal. And finally, I think it is also very interesting to try to explore this relative binning method further, try to see if we can speed up parameter inference further. So for the second half of my talk, I would like to try to make some contact between my research on gravitational waves and the other major topic, gravitational lensing. It turns out that gravitational lensing of gravitational waves should be expected with forthcoming runs, and there are a lot of new things to be learned from this phenomenon. So in order to explain, I will first quickly introduce the concept of gravitational lensing. So basically, if we have any kind of wave source, the source will generate spherical waves propagating outward. But then on its way, if there's some very massive object, it curves the surrounding space-time, and the wavefront, as it propagates, will be distorted. So by the time the wavefront passes the observer, we will see that the flux coming from the source is changed. So depending on how fine-tuned this alignment is, we can be either in the regime of weak lensing, where the flux only changes by very small amounts, and we need large statistics to measure it, or we are in a strong lensing regime where this change is very dramatic. We can see order unity change in the flux, and we can even see multiple images forming. So I will be focusing this strong lensing regime because this is the regime that we will have the most significant effect, and therefore we can learn a lot about the property of the lens. So how likely that this is going to happen? In the case of gravitational waves, because binary black hole sources are so loud, we are going to be able to detect them from cosmological distances. So at that distances, there's some simple way to estimate the order of magnitude of optical depth. So first of all, in order for strong lensing to happen, usually we just compute so-called critical surface density, which is a function of gravitational constant and the typical distance. If you put the distance to be the horizon distance of the universe, then you get some typical number, 10 to the 8 solar masses per square kiloparsec. Now, this is a very interesting number. If a lens has a surface density higher than this number, then it is able to produce strong lensing. We know that currently most of the mass, substantial amount of mass, is locked in galaxy-sized halos, and at the center there sits a typical galaxy. So if you consider the center of this system, then typically we have something like 10 to the 8 solar masses enclosed within the inner 1 kiloparsec that satisfy this condition of supercritical surface density. But then the whole halo is much more extended, enclosed much more mass. So then in the universe, this suggests that these galaxies, they're really like islands that stick out of the ocean. And it is at these places that strong lensing can happen. And typically the optical depth will just be the fraction of mass that sits on this island, which give you something like 10 to the minus 4. But then this is some a priori probability. The actual detected fraction of lensed events will be enhanced by the so-called magnification bias factor, because you are more likely to see brighter events, and lensed events, typically they're magnified. So when we talk about this lensing phenomenon by extremely massive lenses, we can use the picture of geometrical lensing. In this case, the characteristic Schwarzschild crossing time scale is much longer than the period of the wave. So this is the case if the lens is a galaxy or a galaxy cluster. But then, so in this case, we form different images. And these different images are characterized according to whether or not they are the minimum point, saddle point, or maximum point of time delay functions. In the other regime where the Schwarzschild time scale is comparable to the wave period, we have to account for wave diffraction effects. So in this case, we can have even more complicated phenomenon, and the effect on the wave must be computed using some diffraction integral. Now, in the geometrical regime, what happens to gravitational wave is very simple. If you just have two images, then these two images will arrive at different times, appearing as two independent events. and they will have identical frequency chirping, but then they just have different amplitudes. So in this case, we were the first to point out that actually for black hole events, we can never figure out that this is a magnified event. Instead, we will just use our knowledge of the cosmological relation between luminosity distance and redshift and infer a round mass for the system and infer a round source redshift for the system. So, so here, this has some interesting consequences if one wants to interpret population properties by combining a large number of detected events. So for example, here we compute, imagine at a given sensitivity level, what would be the mass distribution of all detected events. So we will have some we will have some distribution expected from whatever source model we have. But then, typically, these source models, they predict that black holes will not cannot form beyond some mass cutoff, or at least the number of sources will drop very quickly. But then, because of gravitational lensing effect, some of the low mass events, they will be substantially magnified, and we will misinterpret them as very heavy events. So then we will have this extended tail. If we want to make any statement about, for example, what is the exact mass cutoff due to this pair instability supernova effect, or we want to judge if this small population of very heavy events, do they hint at a population that formed through dynamic formation, so that you can form second generation, third generation sources, very heavy sources. Then we really need to account for this effect. And similarly, if we have demagnification rather than magnification, then the effect goes the other way. We might find a very strange, extremely high redshift events, and sources that have extremely light masses. Now, it turns out that apart from this more familiar geometrical lensing, gravitational lensing of gravitational waves has more interesting phenomena. And the reason is that gravitational waves has a wavelength that is orders of magnitude longer than what we typically observe with electromagnetic waves. So very often we can be in a regime that wave diffraction effects is very important. Then one very intriguing effect that has origin in wave mechanical effects is the so-called Morse phase. So naively, you would just expect that there's a magnification of the wave. But then it turns out that there's also a topological phase shift of the wave, which really depends on the type of images. So by image types, this is what I have described. Some depending on what kind of extremal points a given image corresponds to in terms of the minimum point or saddle point or the maximum point of the time delay function. Then you have this discrete jump of phases. Now these phases, it turns out that for gravitational waves, you would just infer a wrong orbital phase for the sources. Now you must be wondering, like, what is so interesting about this orbital phase? Usually we don't care about them. Actually, this is a subtle signature that allows you to identify if two events actually are consistent with being gravitational lensed multiple images. So to understand this, let us first understand what determines the phase we measure from the signal in the detector. So this phase, first of all, it depends on intrinsic properties such as orbital phase. for obvious reasons. But then it also depends on other extrinsic parameters, such as at the time of the event, what is the orientation of the detector, and what is the the source inclination and so on. So usually we are not able to measure the orbital phase for individual events very well because it is really degenerate with other parameters. But then we realize that if we want to test the hypothesis that two individual events, they come from the same source due to lensing, we still can't measure the orbital phase individually, but we can measure the difference in the orbital phase very well, and therefore probe the effect that I have described in the previous slide. So just imagine that for each event, we can measure the phase in the detector very well, which is a function of the orbital phase and other intrinsic parameters, extrinsic parameters. And then, in order to test the lensing hypothesis, we require that these parameters are identical. So then, by fixing these two well-measured phases, we can measure the difference in the two. And as I have mentioned, the difference must take discrete values. If lensing is the reality, and it should take random values if these two events are actually unrelated. So this is very interesting because it means that whenever gravitational lensing happens with multiple images, we have a lot of information that allows us to reconstruct the lenses. For example, time delays, magnification ratios, and then these image types, which allows us to determine the configuration of the lens source system. So what is so interesting about this? It is interesting because imagine we can lens the multiple gravitational waves, and then by making use of all of this information, we might be able to, within the very small patch on the sky that we can localize the source, we find the correct lens and the source system. And by doing a detailed lens modeling using optical data, we might be able to actually localize which host the galaxy the source is coming from, and even in which part of the galaxy the source is located at. So in my point of view, this might be the only way, giving our prospect of future observation of gravitational waves, this might be the only way that we can localize a binary black hole mergers and therefore learn something about its astrophysical origin. Another very interesting application is that whenever a gravitational wave is lensed by an intervening galaxy, it has an enhanced probability to get perturbed by some substructure in the lens galaxy, structure that we normally don't see with visible light. For example, this structure might just be the non-luminous subgalactic dark matter halos that are predicted in our standard theory of dark matter, but cannot really host the stars in order for us to see them. So these structures usually is still very difficult to probe with lensing because their surface density, as I have explained before, is typically smaller than the critical density in order to produce multiple images. But the wave mechanical effects allows us to be able to lose a little bit this constraint and be able to probe this ratio called kappa that is not close to 1, but maybe at the level of maybe a fraction of 1. So to explain more, in this case, let's consider the most general outcome. The observed gravitational waveform, once expressed in the frequency space, will be the intrinsic waveform multiplied by an amplification factor. But then this time, this factor is frequency dependent. This factor is a complex number. It not only tells you the amplification, but also the phase shift. Both are functions of frequency now. So if we consider these subgalactic perturbers, even though their effect is not very dramatic, as dramatic as to produce multiple images and perturb the flux by a lot, they can still produce subtle effects that allows detection. So for example, here, I just give one example that the wave is lensed by a subcritical lens. So you have to really squint your eyes to see that the lensed waveform and the unlensed waveform is different. But then if you zoom in, you see the effect of amplitude and phase modulation as a function of frequency. So luckily, if we do match filtering, we can actually detect this subtle effect by comparing the likelihood for both models. So there's a practical problem in this application, which is it is not a priori known what is this expected modulation factor, because it depends on a lot of parameters that we don't really know. For example, the lens profile, distance to the lens and to the source, the impact parameters, and so on. So it may not seem practical to have a parametrized model and search for all possibilities and make sure that we don't miss a signal. So another thing is, if you look for many different signals, you must be able to quantify the look elsewhere effect, because you might just find a fake signal by chance. So in order to solve this problem, we come up with a practical and efficient solution which we hope can be applied to forthcoming data. And it's really something that is very efficient. So the idea is that let's just do it in a model independent way. So imagine that you have find a best fit using the unlensed waveform, and now the lensed waveform will just be some mild departure from that. But then we are making use of the fact that the physical departure usually will be a smooth function of frequency. It will be some curve. This is the departure from 1 for this amplification factor, and it will be some smooth function. But then random noise typically will be uncorrelated between different frequencies. It will be fast oscillating and really random. So then you can try to consider all possible departure curves, and then you marginalize over all possibilities and compute some score. But then you give very clever priors to different curves. Those curves that are more likely reflect a signal will be given a higher prior, and those jagged curves, you will disfavor them. So in this way, you can compute this marginalized score, and then you can do injections to derive what will be the expected distribution if there's no lensing at all, just random noise. So in this way, you can you can really find a significant signal and quantify the significance. And what is more, if there's enough signal-to-noise ratio, you can even reconstruct what is the actual modulation signal and then compare with your theoretical model. So this method is very fast, very efficient to run, and I really hope that once we detected these events in large numbers, we can apply this method. Okay, I think it's time for me to just wrap up. So regarding, I have given a summary of the first part of my talk, and here I will just give some outlook for gravitational lensing of gravitational waves. So basically, it will be expected that in forthcoming observing runs at fully upgraded LIGO Virgo detectors, we may be expecting order unity lensed multiply imaged events per year. So this kind of phenomenon will happen for sure, because we know that there are lenses in the universe, we know that there are sources in the universe. And then it would be very interesting if we can find them in the data by looking for similar gravitational wave events. And it would be very interesting if we can follow up with electromagnetic observations and try to locate the lens source system. And as I said, this might be the only way eventually that we can identify binary black hole mergers to its actual host system. And then once such systems are found, such examples are found, there's a prospect that we might be seeing the signature of substructural lensing in the form of wave diffraction signals. And I have described a very practical way to actually extract this wave diffraction signal from the data. So I think search for this possible signature of wave diffraction by these small lenses is very important, because it will give us another piece of evidence that these things exist, and therefore we can derive constraint on dark matter models. So I think there's a lot of interesting things we can do in the future regarding the lensing of gravitational waves. Okay, I think my presentation will stop here.